Okay, so here is a quick skills check regarding the different types of domain restrictions we will have in rational functions: vertical asymptote, horizontal asymptote, and whole. So I'm going to go through and find each of these. So if you know how to find one, you just want to confirm your answer, just fast forward a little bit. It'll be a relatively quick video. Okay, so I've gone ahead and factored the numerator and denominator. So notice a few things here. When I pull out the 2 in the numerator, I have a difference of squares. You cannot miss those things because that will change your answer. So I see here I have my domain. I'm going to write that first. Even though that's not being asked of me, we should get in the habit of knowing what this is. You don't have to list x twice. I did. That's fine. So the next thing I'm going to do is I'm going to find the vertical asymptotes. So the vertical asymptote is when we have a factor that is in the denominator but not in the numerator. So x minus 3 is, or x is equal to -3 is my vertical asymptote. My whole is going to be the factor that's common, and I think one of the videos I drew a circle over these guys to show the whole, and a little trick to maybe help see what it is. So x is equal to 2. The horizontal asymptote, we have degree 2 over degree 2, which is same over same. So that means I take the leading coefficients. I'm actually going to look at the original problem, and I have a 2 here and a 1 here. So the horizontal asymptote is at y is equal to 2. So these are all the guys that I need, and now I'm going to go ahead and graph them. So I'm going to draw a really generic graph here, and just kind of put in these pieces and then see if I can actually graph what the function looks like, and talk about how we could do that without a calculator. And so I'm going to go ahead and graph vertical asymptote first. That's at -3. So we have vertical dashed line. And I'm going to graph the horizontal asymptote, which is at y is equal to 2. And we know the general behavior of a graph. So I'm running out of room here, so I'm going to start moving some of this stuff up. We don't need it anymore. Oh, that is locked. 1 second here. If I was going to graph this without a calculator, I would use a table. And I know I have a whole at 2. So I'm going to try and see what the behavior is of the graph. Because I have a hole at 2, I know I'm going to have some of the graph down here. And the quadrants are always kitty corner. They're in opposite corners. So that means I should have a picture down here and a picture up here. So I'm going to work on this. And so I'm going to plug in, I know 2 is going to be a whole, so I'm going to plug in 1. So I'm going to plug in 1 for x, and I'm going to see what I get. Well, if I plug in 1 for x, we can go back up to our equation, and we can see that if I plug in a 1, we can use the original. We'll do some math here, and we'll get an answer. Okay, so I created a table. I plugged a few values in, and we have these values. And so I'm going to plot the points. I know 2 is a whole, so these guys right here kind of tell me what's going on around the whole. So I'm going to plot the points. So at 0 I have 4/3, so 1 1/3. So we're here. At 1 we're at 3/2, or 1 1/2. And at 2 we have a whole, so I'm going to draw that whole. So we kind of see what's happening here. It's increasing from 0 in this direction. And so which means at -1 I have 1 here, so we're going to be decreasing. This gives me that general pattern that we know is going to exist for a rational function. And as I said, there's always a reflection into the opposite quadrant on the other corner. And so we can just generically draw that right there. And there's our graph without using a calculator.